Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. The ocean has never been silent. For millions of years, its depths have resonated with a natural symphony. The rumble of underwater earthquakes, the crash of waves, the songs of whales echoing across hundreds of kilometers, and the crackling of coral reefs bustling with life. This acoustic environment, this soundscape, has shaped marine life in profound ways, influencing how creatures communicate, find food, navigate vast distances, detect predators, and find mates. But over the past century, and particularly the last 50 years, a new voice has dominated these waters: humanity's industrial footprint. The soundscape of our oceans is transforming, becoming increasingly dominated by anthropogenic or human-generated noise. Marine scientists have documented this transformation with growing alarm, measuring sound levels that have doubled in many regions each decade since the 1970s. What we're witnessing is essentially an acoustic bleaching of our oceans, explains Dr. Maya Rodriguez, marine acoustician at the Scripps Institution of Oceanography. Just as coral bleaching represents a visual indicator of ecosystem distress, rising noise levels are an auditory warning sign, one that we can't afford to ignore. Marine organisms have evolved over millions of years in an acoustic environment that remained relatively stable until the advent of industrial shipping in the early 20th century. The sounds that fill today's oceans would be unrecognizable to marine creatures from just 2 centuries ago. This unprecedented change is happening at a speed that leaves little time for evolutionary adaptation. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe, it's free, and it helps us grow this community together. The sources of this noise pollution are diverse and pervasive. Commercial shipping traffic produces a constant low-frequency drone that blankets entire ocean basins, with over 90,000 large vessels traversing our seas at any given moment. Seismic airgun surveys, used primarily for oil and gas exploration, generate explosive sounds that can travel thousands of kilometers. Military sonar systems emit powerful pulses that reach into the deepest ocean trenches. Offshore construction, including the pile-driving activities required for wind farm development, creates repetitive concussive sounds that reverberate through the water column. Unlike other forms of ocean pollution, noise leaves no visible trace. There are no dramatic oil slicks, no floating plastic patches, no dying coral to photograph. This invisibility has contributed to its relative neglect as an environmental concern, despite mounting scientific evidence of its harmful effects. Sound travels approximately 4 times faster in water than in air, and marine creatures rely on acoustics far more than their terrestrial counterparts. The ocean is primarily an acoustic world, notes Dr. Christopher Harrison of NOAA's Ocean Noise Reference Station Network. Light may penetrate only tens or hundreds of meters in clear water, but sound can travel effectively for hundreds or even thousands of kilometers. For many marine species, sound is the primary sensory modality. It's how they experience their world. The baseline of ambient ocean noise in the North Pacific has risen by approximately 3 decibels per decade since the 1960s, representing a doubling of acoustic power every 10 years. While these numbers might seem abstract, their biological implications are concrete and increasingly well documented. From the largest whales to the smallest invertebrates, marine life is showing signs of stress from this unprecedented acoustic assault. In the perpetually dark depths beyond sunlight's reach, sound reigns supreme. Even in shallower waters, where visibility rarely extends beyond 30 meters, acoustic signals carry critical information across distances that light cannot traverse. The evolutionary adaptations of marine species reflect this reality, from the specialized sound-producing organs of fish to the extraordinary echolocation capabilities of toothed whales and dolphins. Baleen whales, such as blue and fin whales, communicate over vast oceanic distances using low-frequency vocalizations. These acoustic signals, often below the threshold of human hearing, can potentially travel across entire ocean basins when conditions are favorable. The haunting songs of humpback whales, complex compositions that evolve over time in what scientists have termed cultural transmission, serve critical reproductive functions, with males singing primarily to attract females and establish dominance hierarchies. When we record humpback songs, we're essentially eavesdropping on an acoustic courtship ritual that has evolved over millions of years, explains marine bioacoustician Dr. Elena Moretti. These aren't just beautiful sounds, they're evolutionary. Adaptations crucial for the species' survival. Toothed whales and dolphins have evolved sophisticated biosonar systems that outperform any human-made technology in complexity and precision. Sperm whales emit directional clicks that allow them to detect squid at depths exceeding 1,000 meters in complete darkness. Dolphins can identify a fish the size of a golf ball from over 100 meters away, distinguishing between different species based on the acoustic properties of their swim bladders. But it isn't just marine mammals that depend on sound. Over 800 species of fish produce sounds for communication, using specialized muscles that vibrate against their swim bladders or by grinding their teeth. Coral reef fish have been shown to navigate back to their home reefs as larvae by following the characteristic crackling sounds produced by healthy coral ecosystems, a phenomenon known as acoustic wayfinding. Even invertebrates, from snapping shrimp to mollusks, produce and respond to acoustic cues. The collective sound of snapping shrimp, which stun prey with cavitation bubbles produced by their specialized claws, creates a persistent background crackling that dominates shallow water soundscapes in tropical and subtropical regions. Recent research has revealed that larval crabs and other crustaceans use these sounds to identify suitable settlement habitats. The more we study marine ecosystems, the more we realize how fundamental acoustic cues are to their functioning, says Dr. Samuel Richardson, who specializes in coral reef acoustics. Sound provides critical information about habitat quality, predator presence, mating opportunities, and food availability. It shapes behavioral decisions across all levels of marine food webs. The temporal patterns of these sounds are equally important. Dawn and dusk choruses, periods of increased acoustic activity, occur in marine environments just as they do in terrestrial habitats. These daily cycles have evolved over evolutionary timescales, creating acoustic niches that minimize overlap between species competing in the same soundscape. Marine creatures have adapted to recognize not just the characteristics of important sounds, but also their timing and context. This acoustic sophistication extends to the ability to filter relevant signals from background noise, an ability known as the cocktail party effect in humans. However, this filtering has limits that evolved based on the ocean's natural ambient sound levels. When anthropogenic noise pushes those levels beyond evolutionary precedent, these finely tuned acoustic adaptations begin to fail. Marine species are acoustically adapted to an environment that no longer exists in many places, Dr. Moretti explains. It's as if we've changed the rules of a game that these animals have been playing successfully for millions of years, and we've changed them practically overnight in evolutionary terms. The impacts of ocean noise pollution operate through multiple pathways, affecting marine life across various temporal and spatial scales. Scientists categorize these effects into 4 primary mechanisms: masking, behavioral disruption, physiological, stress, and direct physical injury. Masking occurs when anthropogenic noise interferes with the detection and interpretation of biologically significant sounds. For species that communicate acoustically, masking reduces the effective range over which individuals can exchange information. Mathematical models suggest that the communication range of North Atlantic right whales, a critically endangered species that relies on low-frequency calls, has decreased by approximately 80% due to shipping noise in their habitat. Imagine trying to have a conversation at a loud party. You have to move closer together or shout to be heard, explains Dr. Luciana Ferreira, who studies acoustic communication in marine mammals. But marine animals can't simply move closer. In many cases, a female right whale might miss the mating call of a male that, in pre-industrial oceans, she would have detected from 20 kilometers away. Similar masking effects have been documented in fish, which use acoustic signals to coordinate spawning aggregations, and in larval reef organisms that depend on habitat-associated sounds to guide settlement decisions. When these acoustic cues become masked by anthropogenic noise, recruitment rates decline, with potential long-term consequences for population dynamics and ecosystem structure. Behavioral disruption represents a second mechanism of harm, as animals alter their normal patterns of activity in response to noise. Research vessels using underwater microphones have documented cetaceans abandoning feeding grounds during seismic surveys, with displacement distances exceeding 100 kilometers. In some cases, these disruptions can have energetic consequences, particularly for species already stressed by other anthropogenic pressures, such as climate change or reduced prey availability. Controlled exposure experiments have revealed that beaked whales, a group particularly sensitive to acoustic disturbance, show marked changes in diving behavior when exposed to military sonar. These altered dive profiles, characterized by unusually rapid ascents, are consistent with the pathological findings in whales that have stranded following naval exercises, suggesting a causal link between acoustic disturbance and these mortality events. What's particularly concerning is that even relatively modest behavioral changes, if sustained over time, can have significant population-level consequences, notes Dr. Victor Agarwal, population ecologist specializing in marine mammals. If noise causes a nursing female to reduce her foraging efficiency by just 10%, that translates to less milk production, reduced calf growth rates, and ultimately lower reproductive success. Physiological stress responses represent a third pathway of impact. Marine mammals exposed to ship noise show elevated levels of stress hormones, including cortisol and catecholamines. Chronic elevation of these hormones can suppress immune function, impair digestion, and reduce reproductive success. European lobsters exposed to ship noise in laboratory conditions exhibit elevated oxygen consumption and reduced immunocompetence, indicating metabolic costs associated with acoustic disturbance. Perhaps most dramatically, intense sounds can cause direct physical injury. Necropsy results from mass stranding events involving beaked whales have revealed gas and fat emboli similar to decompression sickness in human divers, suggesting that acoustic disturbance can disrupt normal diving physiology. At closer ranges, the pressure waves from intense sound sources like explosions or pile driving can cause barotrauma in fish, damaging gas-filled organs such as swim bladders and causing internal hemorrhaging. There's a dose-response relationship here, Dr. Ferreira explains. Brief or infrequent exposure to moderate noise levels might cause temporary threshold shifts, essentially temporary hearing loss, while longer or more intense exposure can lead to permanent threshold shifts or even direct tissue damage. Laboratory studies have demonstrated that high-intensity sound exposure can damage the hair cells of the fish inner ear, structures fundamentally similar to those in human cochlea. Unlike mammals, many fish species can regenerate these cells, but the process takes time, leaving affected individuals vulnerable during the recovery period. The consequences of ocean noise pollution extend far beyond individual organisms, cascading through food webs and ecological communities in ways that scientists are only beginning to understand. These ecosystem-level impacts often manifest through subtle but far-reaching changes in species interactions, habitat utilization, and energy flow. Predator-prey dynamics are particularly vulnerable to acoustic disruption. Many predatory fish rely on sound to detect prey, while prey species use acoustic cues to avoid predators. Experimental studies in controlled environments have shown that noise exposure can reduce predator avoidance behaviors in various species, potentially increasing mortality rates among affected populations. When we introduce noise into these carefully balanced systems, we're essentially adding a new form of sensory pollution that benefits some species at the expense of others, explains Dr. Rachel Chen, marine ecologist at the University of British Columbia. In some cases, acoustic disturbance may create what we call predation release, where noise disproportionately affects predator foraging efficiency, allowing prey populations to increase. In others, it may have the opposite effect, making prey more vulnerable. Coral reef communities provide compelling examples of these complex dynamics. Healthy reefs produce a characteristic crackling sound, what scientists call the chorus of the reef, generated primarily by snapping shrimp and the feeding activities of fish. This acoustic signature attracts settlement stage larvae of many species, including corals themselves, facilitating recruitment processes essential for reef resilience. When anthropogenic noise masks these settlement cues, it can disrupt recruitment patterns across multiple trophic levels. Laboratory experiments have demonstrated that boat noise can reduce settlement rates of reef fish larvae by up to 40%. Over time, these recruitment failures can alter community composition, potentially favoring species less dependent on acoustic cues for habitat selection. Foraging efficiency represents another vulnerable ecological process. Harbor porpoises, which use high-frequency echolocation to hunt, show reduced prey capture success when exposed to shipping noise. Similarly, European eels catch 40% fewer prey items when subjected to ship noise in experimental conditions. These reductions in foraging efficiency can have knock-on effects throughout food webs, particularly when keystone predators or important herbivores are affected. It's not just a matter of individual species being disturbed, notes Dr. Chen. It's about how these disturbances propagate through ecological networks. When a top predator's foraging efficiency decreases by 30%, that has implications for everything it eats, and everything that eats it. Migration patterns, which often follow acoustic corridors defined by natural soundscapes, are similarly vulnerable to disruption. Gray whales migrating along the Pacific coast appear to deviate from traditional routes to avoid areas of intense noise, potentially increasing energetic costs during already demanding long-distance movements. Migratory fish such as salmon, which use acoustic cues to navigate to natal streams, face similar challenges in increasingly noisy coastal environments. Habitat compression, where noise effectively reduces the usable habitat available to sensitive species, represents a subtler but potentially significant impact. Research in national marine sanctuaries has documented cetacean avoidance of traditionally important feeding areas during periods of elevated noise, effectively reducing carrying capacity in these protected regions. We're essentially seeing an acoustic form of habitat loss, explains marine spatial ecologist Dr. Marcus Novak. It doesn't show up on satellite imagery or habitat maps, but when noise makes 30% of a critical habitat unusable or suboptimal, the ecological consequences can be just as severe as physical habitat destruction. Perhaps most concerning are potential synergistic interactions between noise pollution and other stressors affecting marine ecosystems. Experimental work suggests that organisms experiencing physiological stress from ocean acidification or warming temperatures show heightened sensitivity to acoustic disturbance. These interactions create the possibility of ecological tipping points where multiple stressors combine to produce effects greater than the sum of their individual impacts. Understanding ocean noise pollution first requires measuring it, a technical challenge that has driven rapid advances in marine acoustics over the past 2 decades. From autonomous underwater gliders to fixed hydrophone arrays on the seafloor, scientists have deployed increasingly sophisticated technology to characterize the ocean's changing soundscape. The U.S. National Oceanic and Atmospheric Administration, NOAA, maintains the Ocean Noise Reference Station Network, a system of 12 calibrated underwater listening stations distributed across U.S. marine waters. These stations continuously record ambient sound levels, creating baseline data critical for tracking long-term trends and identifying emerging hotspots of acoustic concern. These reference stations are essentially the ocean's equivalent of air quality monitoring networks, explains Dr. Layla Washington, director of NOAA's Ocean Acoustics Program. They give us standardized measurements that allow us to track changes over time and space. Without this baseline data, we can't effectively manage what we can't measure. Complementing these fixed stations, mobile acoustic platforms provide higher spatial resolution. Wave gliders, autonomous surface vehicles powered by wave energy, tow hydrophone arrays that can survey large areas more efficiently than ship-based methods. These robotic sentinels are particularly valuable in remote regions where deploying and maintaining fixed infrastructure would be prohibitively expensive. Passive acoustic monitoring has become an essential tool for marine protected area management, allowing scientists to detect the presence of vocalizing species without direct observation. Arrays of hydrophones can triangulate sound sources, revealing how animals move through and utilize protected habitats. This information helps managers assess whether established boundaries adequately protect acoustically sensitive species from anthropogenic disturbance. The ocean is opaque to light but transparent to sound, notes Dr. Washington. Passive acoustics gives us ecological insights that visual surveys simply cannot provide, particularly for deep-diving species or those active at night. It's like having ears in the ocean 24 hours a day, 7 days a week. The technology for sound measurement continues to advance rapidly. New digital signal processing techniques allow for automatic detection and classification of both biological signals and anthropogenic noise sources. Machine learning algorithms can now identify individual whales based on their vocalization patterns, enabling population monitoring at unprecedented scales. Mapping ocean noise presents unique challenges compared to terrestrial soundscapes. Sound. Propagation in water depends on complex factors, including temperature, salinity, depth, and seafloor composition. Advanced acoustic propagation models integrate these variables to predict how noise from shipping lanes, offshore construction, or seismic surveys will affect different areas and depths. The same sound source might be barely audible 10 kilometers away in one environment, but clearly detectable at 100 kilometers in another, explains acoustic oceanographer Dr. Thomas Ruiz. These propagation models help us understand which habitats are most vulnerable to particular noise sources and inform mitigation strategies accordingly. International efforts to standardize ocean noise measurement have gained momentum through the International Quiet Ocean Experiment, IQOE, a scientific initiative coordinating research across national boundaries. Standardized metrics allow for meaningful comparisons between regions and time periods, helping to identify global patterns and trends. Scientists increasingly recognize the need to correlate acoustic data with biological observations to establish dose-response relationships. These connections form the scientific foundation for evidence-based regulation and management. Controlled exposure experiments, where researchers measure physiological and behavioral responses to standardized sound stimuli, help establish causality between noise exposure and observed effects. The gold standard is to simultaneously record both the noise and the animal's responses, says Dr. Ruiz. This allows us to move beyond correlation to causation, which is essential for effective policy development. Despite the pervasive nature of ocean noise pollution, effective solutions exist across technological, operational, and regulatory domains. Unlike many marine environmental challenges, noise pollution stops when the source is silenced, leaving no persistent legacy contaminants in the environment. This characteristic offers hope for rapid ecosystem recovery when appropriate mitigation measures are implemented. Ship quieting technologies represent one of the most promising approaches for reducing the dominant source of ocean noise pollution. Modern propeller designs can significantly reduce cavitation, the formation and collapse of vapor-filled bubbles that produce much of a vessel's underwater noise signature. Other innovations include vibration-isolated engines, hull optimization, and specialized acoustic dampening materials. The technology to make ships significantly quieter exists today, notes naval architect Dr. Elena Costura. Historically, this technology was developed for military applications, submarines and surface vessels designed to evade sonar detection. But we now see increased interest in adapting these quieting techniques for commercial shipping. Economic incentives are helping to accelerate adoption of these technologies. Several major ports, including Vancouver and Hamburg, have implemented fee discount programs for quieter vessels. These programs use underwater listening stations to verify noise performance, rewarding ships that meet specified criteria with Reduced harbor fees. The growing market for quiet ships has prompted classification societies to develop notations specifically for underwater radiated noise, similar to existing energy efficiency ratings. Operational measures complement technological solutions. Reducing vessel speed has emerged as a particularly effective approach, with studies demonstrating that a 10% speed reduction can decrease acoustic output by approximately 40%. Traffic separation schemes that route shipping away from biologically sensitive areas provide another operational tool, creating acoustic refugees where natural soundscapes can prevail. We've seen this approach work successfully in the Harrow Strait region of the Salish Sea, explains Dr. Marcus Thompson, who studies whale behavioral responses to ship noise. When vessel traffic was rerouted away from critical killer whale feeding grounds, we observed immediate improvements in their foraging efficiency and social interactions. For impulsive noise sources like seismic surveys and pile driving, temporal restrictions offer effective mitigation. Scheduling these activities outside breeding seasons or migration periods can significantly reduce their biological impact. Technical alternatives are emerging as well. Marine vibrosize technology, which uses sustained vibrations rather than explosive airgun pulses for seismic exploration, produces less environmental noise while providing comparable geological data. Bubble curtains represent another promising mitigation technology for construction noise. These systems release compressed air through perforated pipes surrounding a pile driving site, creating a wall of bubbles that attenuates sound transmission. Field tests have demonstrated noise reductions of up to 15 decibels, representing a 30-fold decrease in acoustic energy when properly deployed. Regulatory frameworks have evolved significantly over the past decade. The European Union's Marine Strategy Framework Directive explicitly identifies underwater noise as a pollutant and requires member states to achieve good environmental status with respect to noise levels. In North America, the U.S. National Ocean Policy and Canada's Oceans Act provide mechanisms for addressing underwater noise through marine spatial planning and ecosystem-based management approaches. What's encouraging is the shift from treating noise as an incidental byproduct to recognizing it as a pollutant that requires systematic management, says environmental policy expert Dr. Sophia Nakamura. We're moving beyond ad hoc mitigation toward comprehensive strategies that address cumulative impacts across multiple sources. International governance has progressed as well. The International Maritime Organization, IMO, issued voluntary guidelines for ship quieting in 2017, creating a framework for potential future regulation. Regional agreements like the Agreement on the Conservation of Cetaceans in the Black Sea, Mediterranean Sea, and contiguous Atlantic area, ACOBAMs, have developed detailed noise mitigation protocols that serve as models for other regions. As awareness of ocean noise pollution grows, scientists are identifying critical knowledge gaps that must be addressed to inform effective management. These research priorities span disciplines from basic acoustic oceanography to population biology, reflecting the complex and multifaceted nature of the challenge. Among the most pressing needs is improved understanding of cumulative and chronic effects. While acute impacts from intense noise sources are relatively well documented, the long-term consequences of persistent elevated background noise remain poorly understood. Multi-year studies tracking the same individuals or populations over time could reveal these chronic effects, which may be subtle but biologically significant. We're quite good at measuring short-term responses to noise, explains Dr. Isabel Herrera, who specializes in physiological stress responses in marine mammals. But detecting population-level impacts requires decades of consistent monitoring, connecting individual physiological stress to reproductive success and survival rates. That's the missing link in many cases. Acoustic biodiversity represents another emerging research frontier. Scientists are developing acoustic indices, mathematical measures of soundscape complexity that may serve as proxies for ecosystem health and biodiversity. These tools could provide cost-effective monitoring capabilities, particularly in remote regions where traditional biological surveys are logistically challenging. Just as satellite imagery revolutionized our ability to track deforestation and land use change, acoustic monitoring could transform how we assess ocean health, suggests Dr. Herrera. A healthy reef sounds different from a degraded one. We're learning to quantify those differences in ways that scale across large areas. The concept of acoustic resilience, how ecosystems recover acoustically following noise disturbance, represents an important research direction with direct implications for management. Preliminary studies suggest that some habitats recover their natural acoustic signatures within hours after noise cessation, while others require much longer periods. Understanding these recovery dynamics could help establish appropriate buffer times between permitted noise-producing activities. Knowledge gaps exist not only in biology, but also in acoustic propagation modeling. More sophisticated models incorporating three-dimensional oceanographic features would improve predictions of how noise travels through complex marine environments. These advanced models could support dynamic management approaches that adapt to changing oceanographic conditions rather than relying on static buffer zones. Despite these challenges, reasons for optimism exist. Public awareness has grown dramatically, with ocean noise pollution increasingly featured in mainstream media, educational curricula, and policy discussions. Technological innovation continues to advance, with next-generation ships designed for quieter operation beginning to enter commercial fleets. What's particularly encouraging is the growing recognition that quieter operations often align with other environmental and economic goals, notes marine policy analyst Dr. Thomas Chen. More efficient propellers reduce both noise and fuel consumption. Slower vessel speeds decrease both acoustic output and greenhouse gas emissions. These co-benefits create powerful incentives for change. Several success stories demonstrate the ocean's capacity for acoustic recovery when noise sources are reduced. During the shipping slowdown following the 2008 global financial crisis, ambient noise levels in some regions decreased by 6 decibels, a 75% reduction in acoustic energy. More recently, the pandemic-related reduction in maritime traffic in 2020 created an unprecedented opportunity to study natural soundscapes in normally busy shipping lanes. These natural experiments give us a glimpse of what recovery might look like, explains Dr. Chen. The ocean soundscape responds almost immediately when we reduce noise inputs. It doesn't require decades of remediation like chemical contaminants or plastic pollution might. Indigenous knowledge systems are increasingly informing scientific understanding of ocean soundscapes. Coastal communities that have maintained generational connections to marine environments often possess detailed acoustic knowledge that predates scientific monitoring. Partnerships between traditional knowledge holders and academic researchers create opportunities for more holistic approaches to soundscape conservation. As ocean noise gains recognition as a serious environmental concern, interdisciplinary collaboration is breaking down traditional silos between acoustics, marine biology, engineering, and policy. This integrated approach recognizes that effective solutions must address not just the physics of sound, but also the biology of acoustic perception, the engineering of quieter technologies, and the societal frameworks that govern ocean use. The ocean has been speaking to us, concludes Dr. Herrera. Now we're finally learning to listen, not just to the sounds of marine life or the noise we create, but to what these changing soundscapes tell us about the health of our shared blue planet. The question isn't whether we can restore healthier ocean soundscapes, but whether we will choose to do so.